Hello, everybody, and welcome to today's lecture, part of the machine learning lecture series. The topic we're discussing is machine learning in production. My name is Dr. Andrei Holtz, and it's a pleasure to guide you through this topic. Machine learning in production is more than just building models. It's about taking those models and making them work in real-world applications. In this session, we'll explore the life cycle of ML projects, discuss common technical and non-technical challenges, and provide practical insights into building scalable, reliable, and efficient ML systems. Feel free to connect with me on LinkedIn if you would like to discuss this topic further or have any questions after the lecture. Let us get started. Machine learning in production is about translating research breakthroughs into actionable and impactful solutions. However, this transition is far from simple. Challenges like scalability, reliability, and adaptability are critical to address. This lecture is about mastering those challenges, and we're moving on to the agenda. We will start by understanding what is productizing ML and the challenges unique to this phase. Then we'll explore how ML differs from traditional software and break down the ML pipeline, focusing on key components like data management, versioning, and training. Later, we'll discuss strategies for deployment, ensuring scalability, and maintaining performance with monitoring and feedback loops. We will also touch on critical topics like responsible AI and the importance of aligning ML projects with business goals through cost optimization and stakeholder communication. By the end of this session, you will have a comprehensive understanding of how to successfully manage and scale ML projects in production environments. Let us move on. Machine learning is powerful, but its true potential lies in production. This is where research models transform into real-world applications that impact business and lives. However, this transition introduces challenges. Models need to scale, operate reliably, and adapt to ever-changing environments. For example, think about a recommendation engine used by an e-commerce platform. In research, the model might work flawlessly with static datasets. In production, it must handle real-time data streams, adapt to user behavior changes, and function without downtime, all while scaling to millions of users globally. By overcoming these challenges, ML in production transforms theoretical models into impactful tools, delivering value at scale. This is why mastering production ML is critical for anyone looking to create practical and robust AI solutions. Let us talk about challenges that happen in the production ML. First of all, continuous integration of new data. In production, data is not static. Models must be updated regularly to reflect the latest data. For instance, a fraud detection system must constantly integrate transactions data to remain effective against new patterns of fraudulent activity. Handling data drift and distribution shifts. Over time, the data distribution may change, rendering a previously accurate model obsolete. This phenomenon, known as data drift, is especially problematic in dynamic environments like e-commerce or social media platforms. Managing versions of data, models, and code. In production, it is critical to track and manage different versions of data, models, and underlying code. Imagine debugging a production issue. Without version control, it becomes almost impossible to pinpoint what went wrong. Balancing latency, scalability, and reliability. Production ML systems must operate under real-world constraints. A recommendation system for an online retailer must generate results in milliseconds while handling millions of requests simultaneously without sacrificing accuracy. meeting compliance and ethical standards. As regulations around AI grow, compliance is becoming incredibly important. For example, models must align with privacy regulations like GDPR and avoid biases that could lead to unexpected outcomes. Each of these challenges requires not only technical solutions, but also strategic planning. And throughout this lecture, we'll discuss strategies and tools to address these challenges. Let us take a moment to understand how machine learning differs from traditional software development. These differences are fundamental and impact everything from the development approach to the skills required. First of all is the nature of output. Traditional software is deterministic. It executes predefined rules to deliver exact outputs. ML, on the other hand, produces probabilistic outcomes that involve some degree of uncertainty. For instance, a rule based system might classify emails into spam or not spam with hard coded rules, while ML model provides probabilities for each classification. The development approach. Classical software follows a linear, requirement driven process. In ML, the process is data driven, iterative, and experimental. You often tweak models and retrain them to achieve better performance. Quality assurance. Traditional software is tested against functional specifications. For machine learning, validation focuses on metrics like accuracy, precision, recall, F1 score, and a lot of other metrics, using test data sets to measure model performance rather than strict specifications. Maintenance. Traditional systems undergo periodic updates for bug fixes or new features. ML systems require continuous monitoring as the underlying data changes. For example, a recommendation engine might need retraining every few weeks to keep up with evolving user preferences. Skill set required. Classical software development emphasizes system architecture and engineering. ML demands expertise in data science, statistics, and domain knowledge to understand the context behind the data. What about the challenges? While traditional software struggles with scalability and integration, ML faces unique challenges and issues like interpretability, ensuring data quality, and managing ethical concerns. Project lifecycle. Classical software often has a clear start and end, while ML projects are ongoing, as models require updates to remain effective in dynamic environments. These differences highlight why deploying machine learning in production demands a distinct mindset and approach, which we will explore further in this lecture. Let us dive into the specific challenges of ML models. First one is metrics definition. The success of any ML model depends on how we define its objectives. Metrics like accuracy, precision, recall, F1 score, and a lot of others need to align with the problem at hand. For example, in fraud detection, precision might be more critical than recall to avoid false accusations. Baseline model establishment. So, starting with a simple model is essential. A baseline model, such as decision tree or linear regression, or sometimes even like the uh, constant model like rule-based model, provides a benchmark for measuring the improvement of more complex models. Model selection and tuning. Um, with countless algorithms available, choosing the right one and tuning hyperparameters can be overwhelming. Tools like grid search and random search can help automate this process. Debugging and testing. Errors often come from incorrect assumptions, data leakage, or poorly designed features. And testing your pipeline thoroughly helps identify and resolve these issues. Hypothesis testing and experiment tracking. Effective ML development requires running and tracking experiments systematically. Tools like MLflow or weights and biases help manage this complexity. Again, you need to highlight this. You must track every experiment in machine learning. Otherwise, you are not developing it data in a data-driven way. Interpretability, responsibility, and reliable ML or ethical ML. As ML systems impact people's lives, it is critical to ensure that models are interpretable and unbiased. For example, lending models should not unfairly disadvantage certain groups. Data quality, quantity, and availability. ML models are only as good as the data they are trained on. Low quality or insufficient data can lead to inaccurate predictions. Data augmentation or synthetic data generation can sometimes address this issue. But you should be very cautious with augmentation and synthetic data since you might introduce biases. Lack of domain knowledge. ML engineers often lack domain knowledge, which can result in poorly designed features or misinterpreted results. Collaborating with domain experts is key to bringing this gap. And each of these challenges require careful planning and the right tools to address. By systematically working on those challenges, you can significantly improve the development and deployment of ML models. Let us break down the stages in the ML pipeline, which is the foundation of every machine learning project. Each stage is interconnected, and success at one stage often depends on how well the previous stage was executed. The first one is data management and pre-processing. This is where everything begins. Raw data is collected from various sources, and pre-processing involves cleaning the data, handling missing values, removing duplicates, and normalizing formats. For example, in a credit scoring system, inconsistent formats in customer data must be standardized before analysis. Feature engineering. Once the data is cleaned, we move to identifying or creating features that can improve model performance. For instance, creating a spending to income ratio uh, can make a good feature for a credit scoring model and make this model more predictive. Experimentation and model building. In this stage, multiple algorithms are trained and evaluated. Hyperparameter tuning is key here. Tools like grid search, random search, or any other automated systems help improve this process or automate it. For example, you might try different configurations of neural network to find the best one. Model validation and testing. Before a model goes into production, it needs thorough testing. Metrics like accuracy, precision, recall, F1 score, and any other metrics provide insights into how well the model performs. And this step ensures that the model is reliable and ready to be deployed for real world. And the deployment. This is where the model transitions from the lab to production. Deployment often involves integrating the model with existing workflows or user-facing applications. For instance, deploying a chatbot might require exposing the model via API, monitoring and feedback loops. Even after the deployment, the work isn't over. Continuous monitoring ensures the model maintains performance over time. If there is a data drift, like user behavior changes in a recommendation system, feedback loops help trigger retraining to adapt to new conditions. And by following the stages methodically, you can ensure a robust and scalable machine learning solution that delivers consistent value. If we take a look at the machine learning part of the whole solution, like whole production solution, well, the core ML part, like the model itself, will be just a small piece of a bigger picture. Productionizing machine learning system involves overcoming several technological and infrastructure challenges. And let's break down some of the most critical ones. Data collection. Data is the backbone of any ML system. Without data, there is no ML. In production, ensuring consistent and timely collection from multiple sources can be challenging, especially when dealing with real time data streams. Data verification. Poor quality data can break any ML system. Data verification ensures that only valid, clean data is used in training or inference. For example, a retail recommendation system might fail if product metadata is incomplete. Feature extraction. Feature engineering is critical for model accuracy, but automating this process while ensuring scalability for large datasets can be challenging and demanding. Process management tools. So these tools orchestrate workflows, enabling the seamless execution of data pipelines, model training, and deployment. Tools like Apache Airflow are commonly used in this space. Configuration. In machine learning, managing configurations such as hyperparameters, data paths, versioning is crucial for reproducibility and debugging. Machine resource management. Allocating computational resources efficiently, especially for large scale training or real time inference, requires careful planning. For instance, GPUs might be prioritized for training while CPUs handle inference. Analysis tools. Um, Debugging and EDA are essential for understanding data issues and improving models. And tools like TensorBoard or Pandas profiling are often used. Monitoring. Once a model is live, monitoring a performance is a must have. Metrics like latency, throughput, and accuracy need to be tracked continuously. Drift detection is also essential to identify when the model requires retraining. Serving infrastructure. Finally, the serving infrastructure supports the deployment of models at scale. This might involve APIs, containerized services, or serverless architectures depending on the application. As shown in the diagram, these components are interdependent. For instance, robust data verification impacts feature extraction, while efficient resource management influences the serving infrastructure. And addressing these challenges systematically is critical to creating reliable production ML system. So as we have mentioned, data is the backbone of every machine learning project. Without it, you cannot model anything. However, working with data comes with its own set of challenges. First of all is the availability. Many projects stall because there's either insufficient data or delays in acquiring it. For instance, a healthcare ML project might struggle to get enough labeled patient records. Collection of the data. Gathering data from diverse sources like APIs, sensors, or datasets requires careful planning to ensure reliability. For example, data scrapped from the web might be inconsistent or incomplete, and storing and versioning. As datasets evolve, it is crucial to track changes over time. Tools like DVC or Lake FS help manage dataset versions to maintain reproducibility. Validation. Validating the integrity and consistency of data is essential. Without proper validations, errors like missing values or duplicates can propagate into the model, leading to inaccurate predictions. Pre-processing. Data rarely comes in a perfect shape. Cleaning, normalizing, and transforming data into a consistent format is a critical step that often takes more time than model development itself. Representation and biases. Data representation can lead to unintended biases. For example, if a hiring algorithm is trained on past biased hiring practices, it may replicate those biases in its predictions. And privacy and regulations. So, legal frameworks like GDPR impose strict rules on how data is collected, stored, and used. Ensuring compliance is both a technical and ethical responsibility. Feedback loop. User feedback can be a gold mine for improving models, but integrating it effectively into retraining workflows requires careful design. And inference and scaling. Real time inference in production environments, such as predicting credit card fraud within milliseconds, places enormous demands on infrastructure. Scalability is key to meeting these requirements. And as illustrated in the comic here, um, ML systems heavily rely on data to deliver results. And if the data quality or quantity is poor, the entire system's performance is compromised. Addressing these challenges systematically ensures a strong foundation for successful ML projects. Error analysis is a critical aspect of developing and deploying machine learning models. It helps us identify where the model is failing and why. Let us explore the key components involved. The first one is data. So, errors can originate from missing or noisy data, unbalanced dataset, or sampling issues. For instance, if a dataset for a language model heavily favors English, it might perform poorly on other languages. Features. Issues in feature engineering, such as selecting irrelevant features or poor scaling, can significantly impact a model performance. An example is using unnormalized numerical data, which can skew predictions. Modal. Algorithmic biases, incorrect parameter tuning, or unsuitable model selection often leads to errors. For example, applying a linear regression model to a highly nonlinear problem can result in poor performance. Post processing. After the model generates predictions, errors can arise during the transformation or interpretation of these outputs. For instance, incorrectly converting probabilities into class labels can introduce significant errors. Forecast. Forecasting errors often accumulate due to issues in previous stages. If there are inaccuracies in data or features, the model's predictions may compound these problems. Let us examine this with visualization. So the benchmark accuracy of the model is 73.8%. This might look reasonable at first glance, but the performance breakdown reveals that performance varies significantly by region. Some regions achieve near perfect accuracy, while others fall as low as 42%. These insights are useful. Instead of blindly improving the overall accuracy, we can focus on addressing the specific regions or components where the model struggles. This might involve collecting more balanced data, refining features, or tweaking post processing methods. Error analysis not only helps improve model performance, but also builds trust by ensuring that failures are systematically identified and addressed. On this slide, we are diving into two fundamental approaches to model evaluation: offline and online evaluation. Offline evaluation focuses on using historical datasets. And here we split data into training and test sets or use techniques like cross-validation. This process allows us to iterate rapidly and evaluate models in controlled environment. For example, it is great for testing different algorithms or parameter configurations. However, it has its limitations. It doesn't always account for new data patterns, seasonal trends, or evolving user behaviors, which can affect real world performance. That is where online evaluation comes into play. This method tests models in live or near live settings, providing insights into how they perform with real users. A classic example is A B testing. Imagine deploying a new algorithm to 10% of your user base while the remaining 90% stick with the old algorithm. Both groups experience the same external conditions, like a holiday season, allowing us to compare metrics fairly. For more advanced experimentation, we can use multi-armed bandit testing. This method dynamically allocates more traffic to the better performing model, while still giving alternative models enough exposure for evaluation. It balances exploration to test different options and exploitation to maximize benefits from the best model. Another method is interleaving, where results from multiple models are presented together in a ranked list. For example, in a recommendation system, items from different models might appear side by side. User engagement, like clicks or purchases, directly reveals which model is preferred. Each method has its strengths, and combining both offline and online approaches is often the most robust strategy. We first validate the model's potential offline, ensuring it performs well on historical data. Then we confirm its real world value through online testing. And this combination minimizes risk and ensures our models are optimized for both past patterns and current user behavior. Let us compare CI/CD for ML and traditional software. This table highlights the critical differences. And the first one is focus. Traditional CI/CD pipelines focus on automating code changes and running functionality tests. In contrast, ML CI/CD must also handle model artifacts and data checks, ensuring that the models and datasets are synchronized throughout the pipeline. Experiment tracking. Experiment tracking is rarely integrated into traditional CI/CD pipelines, which rely mostly on basic version control. ML pipelines require specialized tools like MLflow or DVC, which track hyperparameters, performance metrics, model versions, data versions, and ensure reproducibility. Testing expands significantly in ML workflows. In addition to traditional unit tests and integration tests, ML pipelines include data validation to check for anomalies or drift in input data, and performance checks for the models themselves, such as accuracy, precision, recall, F1 scores, and any other metrics. While traditional software CI/CD produces build outputs like binaries and containers, ML CI/CD artifacts are trained models, data transformations, and feature engineering pipelines, and those artifacts must also be versionized and tested. Pipeline structure. Traditional CI/CD pipelines often follow a straightforward linear process: developed, test, deploy. In ML, the pipeline incorporates additional stages such as data ingestion, feature engineering, model evaluation, making it more iterative and complex. Maintenance. Maintenance in traditional CI/CD typically involves fixing bugs or rolling out version updates. For ML systems, maintenance is an ongoing effort that includes retraining models with new data, detecting drifts, and ensuring that models remain accurate and aligned with evolving datasets. These distinctions underscore why CI/CD for ML requires additional tools, practices, and processes to accommodate the dynamic nature of data and models. By addressing these challenges, we can build ML systems that are both scalable and robust in production. As for the training and experimentation in machine learning, that is an iterative process. Let us walk through some of the best practices and tools that make this process efficient and reproducible. And first of all is iterative training with experiment tracking. When training models, it's vital to track each experiment's configurations and results systematically. Tools like MLflow and weights and biases are designed for this purpose. They allow you to log key parameters such as learning rates and batch sizes and track evaluation metrics like accuracy of F1 score. By maintaining detailed experiment logs, you can compare different models and identify which configurations work best, ensuring reproducibility. Optimize hyperparameters with automated tools. Manually tuning hyperparameters can be time consuming and inefficient. Automated optimization methods like Bayesian optimization or grid or random searches streamline this process. For example, instead of testing every possible combination of hyperparameters, Bayesian optimization narrows down the search space by focusing on promising configurations. This saves both time and computational resources. Establish robust evaluation metrics. Your model's success depends on the metrics you choose to evaluate it. Beyond basic metrics like accuracy, consider metrics Beyond basic metrics like accuracy, consider metrics tailored to your problem. For instance, in a healthcare setting, metrics like recall might be prioritized to minimize false negatives. Using the right metrics ensures that your model aligns with real world objectives. And tools to support the process. MLflow. This tool tracks experiments, log metrics, and even manages model deployments. It's an end-to-end solution for managing your ML lifecycle. Weights and Biases is another powerful platform for tracking experiments, visualizing training process, and managing hyperparameter sweeps. And by adopting these best practices and leveraging the right tools, you can make your training and experimentation process not only more efficient, but also more transparent and scalable. These methods help you iterate faster, deploy better performing models, and ultimately achieve more impactful results. What about the data? As we know, data is the backbone of every machine learning system, and without proper data management, even the most advanced models will fail to perform effectively. Let us break this down. Why data management matters? Managing data involves three critical stages. Collection. Data comes from diverse sources, including APIs, sensors, logs, and databases. For example, a recommendation system might pull user behavior data from app interactions, while a weather model ingests sensor data from IoT devices. Cleaning. Collected data is rarely perfect. Cleaning involves handling missing values, fixing inconsistencies, and normalizing formats to ensure that your data is reliable. For instance, managing data sets from different countries often require resolving inconsistencies in date formats. Versioning. Just as you version your code, datasets also need to be versionized. This ensures reproducibility and helps track how changes in data affect your models. For example, if your model underperforms in production, versioning allows you to trace back and test the dataset used during training. Tools for data management. Well, several tools can help automate and simplify this process. Let's just mention some of them. DVC or Data Version Control. It integrates seamlessly with Git to track and version datasets alongside your code. Git LFS, ideal for managing large files like datasets or model artifacts. LakeFS adds Git-like version control for data lakes, enabling robust management of large-scale datasets. And what about the best practices? Well, automate pipelines. Automating data pipelines ensures consistency and reduces manual effort. For example, tools like Airflow or Perfect can orchestrate data ingestion, cleaning, and transformation tasks. Maintain metadata and logs. Metadata includes details about how the data was collected, processed, and used. Logging this information allows you to have better debugging and compliance with regulations. On this diagram, you can see a kind of ML platform. It illustrates how raw data flows through a pipeline into a feature store, then it's transformed and stored and served for model training and inference. Each step is supported by specific roles, like data engineers, data scientists, and ML engineers, working collaboratively to manage data efficiently. And each of the roles has their own artifacts. Let me show you, like the artifact of the data scientist is like ML model, the artifact of data engineer is like data pipeline, and the artifacts of ML engineer, well, sometimes it's model serving. By prioritizing data management and leveraging the tools, you can ensure reproducibility, scalability, and reliability of your model workflows. And remember, the quality of your data directly impacts the quality of your models. Deploying machine learning models in production involves selecting strategies that balance performance, reliability, and user impact. Let us explore some common deployment options and patterns. As for the options, batch inference. This approach processes large amounts of data at scheduled intervals. It is suitable for non-urgent tasks like generating nightly predictions for a marketing campaign or updating recommendations in a bulk. Batch inference is efficient but lacks real-time responsiveness. real-time inference. It is ideal for applications requiring immediate predictions, like fraud detection or personalized recommendations. Real-time systems prioritize low latency and high availability, but demand more robust infrastructure. As for the deployment patterns, let us discuss some of them. One of the most common is blue-green deployment. This strategy minimizes downtime by running two environments: blue, current production, and green, new version. You route traffic to the green environment once it's tested and stable. If issues arise, you can easily revert to the blue environment. Canary releases. With this approach, the new model or feature is gradually rolled out to a small subset of users. For instance, you might start with 5% of traffic, monitor performance metrics like latency or error rates, and expand the rollout only if results are satisfactory. Feature togglers. These allow you to enable or disable specific features dynamically without redeploying the entire system. This flexibility is particularly useful for A/B testing or for rolling out features incrementally. Dark launches. A silent release to a subset of users or systems allows you to test new features in production without exposing them to all users. This helps catch potential issues early. A/B testing. This approach splits traffic between multiple models or features to directly compare their impact. For example, you might test a new recommendation algorithm, Model B, against the existing one, Model A, to see which drives higher user engagement. Choosing the right strategy. Your choice of strategy depends on your application's requirements. For instance, real-time systems like a chatbot demand immediate inference, making patterns like canary releases or A/B testing more appropriate. On the other hand, batch processing suits non-urgent scenarios like financial reporting. By carefully selecting and combining these strategies, you can deploy models safely, with minimal disruption, and gather valuable insights to refine your system further. Monitoring ML models in production is significantly more complex than traditional system monitoring. Let us examine why by comparing traditional testing and monitoring workflows with those required for ML systems. On the left, you can see traditional system testing and monitoring. In traditional systems, testing focuses on the code itself. The process is almost linear. Unit tests are meant to validate individual code components. Integration tests to ensure that different components work together as expected. And system monitoring tracks metrics like uptime, latency, and throughput to ensure the system remains operational. This workflow works well for deterministic systems where outcomes are predictable. However, ML models are probabilistic and depend on dynamic evolving data, which introduces additional challenges. ML-based system testing and monitoring that you can see on the right. ML systems add several layers of complexity because the model's behavior depends not on just the code, but also on the data and the training processes. Here's how the testing and monitoring pipeline evolves. Data tests to verify the quality and integrity of the input data. For example, checking for missing values, outliers, or corrupted records. Poor data quality can degrade model performance. Skew tests compare the distributions of training data and production data. If there if there is a significant difference, the model may perform poorly. For instance, a recommendation model trained on winter product data might struggle during the summer. Model tests validate the model's accuracy, precision, recall, and other metrics to ensure reliability. This step identifies potential weaknesses in the model's logic. And prediction monitoring. Once deployed, monitor the predictions for accuracy, bias, and drift. For example, it's a fraud detection model, and if it starts flagging an unusual high number of transactions, it could indicate data drift or change in user behavior. System monitoring. Traditional system metrics like uptime and latency remain crucial, but they are now complemented by ML specific metrics. Let me give you a small real world example. Imagine deploying a sentiment analysis model. Traditional monitoring might check whether the system is up and processing requests. ML specific monitoring would also validate whether the model is correctly identifying sentiment and if the input data distribution, like language or demographics, has shifted from the training dataset. And by integrating these additional tests and monitoring layers, we can proactively identify and address issues, ensuring that ML systems remain robust and reliable in production environments. Once a model is deployed in production, monitoring becomes an essential part of the workflow to ensure it continues to deliver reliable and accurate predictions. Let us break down the key elements of monitoring ML models in production. First one is key metrics. To monitor effectively, we track several critical metrics. It's prediction accuracy. If ground truth feedback is available, we can measure how often the model's predictions are correct. This is particularly useful in applications like fraud detection or sentiment analysis. Latency. For real-time systems, latency is a key metric affecting user experience. For example, a recommendation engine needs to respond within milliseconds to maintain seamless interactions. Resource usage. Monitoring CPU, GPU, and memory usage ensures the system operates efficiently and avoids overloading. And data drift indicators. This tracks changes in the incoming data's distribution. For example, if the model was trained on a specific demographic but encounters new data outside the scope, its predictions might become unreliable. And what about the tools? Well, just to mention two of them, Prometheus is a powerful tool for collecting real time metrics from your system. It integrates well with ML pipelines to track performance and resource usage. Grafana is a tool that works with Prometheus to create dynamic dashboards. These dashboards can display trends in accuracy, latency, and drifts over time, making it easy to spot anomalies. You also need alerting mechanisms because monitoring systems need to trigger alerts when something goes wrong. You can do it by setting thresholds. Just set thresholds for performance drops or latency spikes. For example, if prediction accuracy falls below 85%, the system can flag an issue. And alerts can be sent via email, Slack, or like incident management systems like PagerDuty, ensuring the ML team is notified promptly. What about the feedback loops? Monitoring isn't just about detecting, it's also about improving. And you need to collect the user feedback. User interactions such as clicks or corrections can provide valuable data for retraining. For example, in search engine, users clicking on irrelevant results indicate areas for improvement. And Why monitoring matters? Monitoring not only keeps um, you informed, it helps maintain performance and acts as an early warning system. Uh, if the model's accuracy drops or data drift is detected, the ML team can decide whether to retrain the model, roll back to a previous version, or investigate the root cause. And by combining robust tools, real-time alerting, and feedback loops, we ensure that ML systems remain reliable and adaptive in production environments. When we talk about monitoring models in production, we encounter several distinct yet interrelated challenges. Let us explore each of these in details. And the first is data distribution changes. It's one of the first issues we face, covariance shift, when the input feature X begin to differ from the data used during training. A classic example is an e-commerce site during the holiday season where user behavior changes drastically, affecting product searches and purchases. This drift can reduce the model's accuracy unless it's monitored and adapted. Model ownership and production. Without clear ownership, critical updates or fixes can slip through the cracks. So, if no one is accountable for the model's performance, it may degrade over time. Assigning a dedicated team ensures timely interventions and retraining when necessary. And training and serving skew. This occurs when the data processing or feature engineering pipelines used during training do not align perfectly with those in production. For example, a feature normalized differently in production could cause the model to misinterpret data, leading to suboptimal predictions. Model and concept drift. So, model drift refers to a decline in performance as the model encounters new patterns in data. And concept drift occurs when the fundamental relationship changes. For instance, a recommender system trained on old shopping habits might struggle when users shift to new product categories. And both types of drift require active monitoring and regular training. And as for concerned adversaries, sometimes it's fraud. Well, in high stakes environments like fraud detection or spam filtering, adversaries deliberately adapt their tactics to exploit the model. Uh, Attackers may systematically probe the system for weaknesses, making us create updates and some defensive strategies for machine learning models. And pipeline health issues. Data pipelines are the backbone of ML systems, and breaks or errors like a failed ETL or corrupted data feed, they can happen and they lead to dirty inputs, causing predictions or causing faulty predictions or system crashes. And automated pipeline health checks can detect that the data is corrupted or something like this, and those are crucial for ML production. And as for the ML metrics and business metrics, while we measure metrics like accuracy, precision, recall, their impact on business outcomes, well, like sales or user satisfaction, is what truly matters. A model might excel at technical metrics but fail to move the needle on KPIs. Monitoring should include both ML and business metrics for providing a full picture, and extreme events or outliers. External events like sudden spikes in traffic can crush the model into unknown territory. For instance, unexpected surge in queries during a viral campaign may cause unpredictable behavior if the model hasn't encountered similar inputs before. And as for the data quality issues, even minor anomalies in input data, such as missing values, schema changes, or mislabeled examples, can lead to significant errors. Small unnoticed changes like extra column in CSV file can cascade into system-wide issues. And as for the key concepts, at its core, monitoring ML systems involves tracking shifts in a lot of aspects in the data, in the pipelines, in monitoring, in security. And by addressing these challenges with robust monitoring systems, automated alerts, and clear accountability, we can ensure that our models remain reliable, adaptive, and aligned with real world dynamics. Imagine a situation that we are receiving new data and we need to use it to make our models better. And to ensure that our models remain effective in changing environments, we need to update them regularly using the new data. And let us explore like three retraining strategies. The first one is scheduled retraining. This strategy is the most straightforward. We retrain the model at fixed intervals, daily, weekly, monthly, depending on how quickly our data evolves. For example, a weekly schedule might work well for systems like inventory predictions, where patterns change steadily over time. Scheduled retraining is easy to implement but doesn't react to sudden changes in data or performance. Another approach is trigger based retraining. This strategy is more dynamic. Here, retraining is initiated when monitoring systems detect a drop in model performance metric like F1 score or accuracy, or significant data drift where the distribution of incoming data diverges from the training set. For instance, a recommendation system might trigger retraining after a sudden surge in new product listings that weren't part of the original dataset. Trigger based retraining ensures the model adapts to changes promptly but requires robust monitoring and alerting mechanisms. And online learning or like incremental updates. The most advanced approach is online learning, where the model continuously updates itself with the new data in real time. For example, a streaming recommendation system might adjust predictions as user preferences shift throughout the day. While this approach ensures the model stays current, it can be resource intensive and requires careful engineering to avoid overfitting or instability. So, how to choose the right strategy? The choice of retraining strategy depends on resources, data velocity, and domain dynamics. Resources, well, scheduled retraining is resource efficient, but may lag behind real world changes. Online learning demands significant computational and engineering resources. As for the data velocity, high frequency data streams might benefit from online learning, while low velocity domains can rely on scheduled retraining. And rapidly evolving domains like e-commerce or social media might require trigger-based retraining or even online retraining, while static domains like historical archives may need minimal updates. And a hybrid approach often works best. For instance, you might use scheduled retraining for routine updates while leveraging trigger based retraining to handle unexpected changes. And combining robust offline evaluation with real time monitoring ensures retraining decisions are both informed and timely. As user traffic grows or machine learning models become more complex, scalability becomes critical to maintaining performance. Let us explore 4 scalability approaches. Horizontal scaling. This involves adding more servers or instances to the system to handle increased workload. For example, if you're running a model to process millions of requests per second, you might distribute those requests across 10 servers instead of one. Horizontal scaling is effective because it allows you to scale incrementally, adding capacity as demand grows. Load balancing. A load balancer is crucial for horizontal scaling. It sits at the front of your infrastructure and intelligently directs incoming requests to the available servers. This ensures that no single server is overwhelmed and helps maintain consistent response times. For example, in a recommendation system, a load balancer can evenly distribute user queries across multiple nodes. Autoscaling. It dynamically adjusts resources based on traffic or resource usage. For instance, during a flash sale on e-commerce platform, autoscaling can spin up additional servers to handle the spike in user activity, and then scale back down when traffic decreases. This approach optimizes resource usage and minimizes cost during periods of low demand. And specialized hardware. And for computer intensive workloads, especially in deep learning, specialized hardware like GPUs and TPUs can significantly accelerate both training and inference. GPUs are excellent for parallel processing, making them ideal for tasks like image recognition. And TPUs, developed by Google, are optimized for tensor based computations in neural networks, for example, for transformer architecture. These devices enable you to handle large scale workloads efficiently. And how to choose the right approach? Well, the choice depends on factors like cost. Horizontal scaling is more cost effective for general workloads, while GPUs and TPUs come with higher upfront cost but deliver exceptional performance. And performance targets. For real time applications, combining load balancing, auto scaling, and specialized hardware often provides the best balance of speed and reliability. In practice, most systems use a combination of these approaches. For example, an image recognition service might use horizontal scaling and load balancing for general traffic, while reserving GPUs for intensive batch processing tasks. This hybrid strategy ensures scalability without compromising performance or budget. Let's talk about scaling and infrastructure. Scaling is not just about adding resources, it's about leveraging the right infrastructure to handle growing demands efficiently. And let's break this down. Kubernetes is an orchestration tool that helps manage containerized applications at scale. It automates tasks like deployment, scaling, and load balancing for containers. For example, if you are running multiple ML models as microservices, Kubernetes ensures that each service has the necessary resources and scales up or down based on demand. Apache Kafka. Kafka is distributed event streaming platform ideal for real-time data pipelines. It's commonly used for use cases like log aggregation, data ingestion, and streaming analytics. For instance, an e commerce platform might use Kafka to stream user behavior data to an ML model that updates recommendations in real time. There are also serverless options like AWS Lambda, Azure Functions, and Google Cloud Functions. And they allow you to run code without worrying about the underlying infrastructure. These services automatically scale to handle incoming requests, making them a great choice for sporadic or event driven workloads. For example, A fraud detection service could use serverless functions to analyze transactions only when the new data arrives. Scalability features. Auto scaling, and this ensures your system dynamically adapts to workload variations. For example, during a sales event, auto scaling can spin up additional compute nodes to handle traffic spikes and then scale back down. A load balancer distributes incoming traffic evenly across multiple servers, ensuring no single instance is overwhelmed, and this improves system reliability and performance. Imagine deploying a real time recommendation system. You might use Kubernetes to manage the application containers, Kafka to stream live user data, and serverless functions to process occasional computational tasks. Autoscaling and load balancing ensure that the system remains responsive even during peak usage. And by combining these infrastructure tools and scalability techniques, you can build systems that are robust, cost effective, and capable of handling dynamic workloads. As models grow larger and datasets expand, traditional training approaches on a single machine often aren't enough. Distributed training and frameworks provide the tools to scale up model training effectively. And let us take a look at it. So, distributed training divides dataset and computations across multiple nodes or machines. And this is especially critical for deep learning models that require massive datasets and computational resources. Horovod is an open source framework designed for distributed training in TensorFlow, PyTorch, and MXNet. It simplifies scaling by allowing multiple GPUs or nodes to process data simultaneously. Distributed TensorFlow natively supports parallel processing, allowing you to train models across clusters without extensive code changes. For example, a company training a language model like GPT-3 would split the dataset into smaller chunks, each processed by a different GPU or server. Cluster management tools. To coordinate distributed computations, tools like Ray or Desk simplify the process. Ray is built for distributed Python applications and supports machine learning workloads, making it easy to scale tasks like hyperparameter tuning. Desk is another Python based tool that scales pandas, numpy, and other Python libraries across clusters. For example, it can process large datasets in parallel, improving speed and efficiency. And these tools automate the complexity of managing distributed resources, allowing data scientists to focus on model design rather than infrastructure. And what about the cloud platforms? Um, Platforms like AWS SageMaker, Azure ML, and GCP Vertex AI handle the infrastructure side of distributed training, and they offer managed services to automate resource provisioning, provide pre-configured environments, and for instance, SageMaker can seamlessly run distributed training jobs. Azure ML integrates with Kubernetes for advanced orchestration, and Vertex AI specializes in handling both training and deployment workflows. As an example, think about training a recommendation engine for an e-commerce platform and handling millions of users' interactions and product data on single machine would by distributing the training across multiple nodes, the same task can be completed in hours, unlocking faster iterations and deployment. By leveraging these frameworks and tools, organizations can train complex models efficiently, even at massive scales, ensuring they stay competitive in the rapidly evolving ML landscape. Okay, so everything we have discussed so far, monitoring, retraining strategies, scalability, sets the large stage for this slide, which focuses on CI/CD and automated ML pipelines. And these pipelines form the backbone of a reliable and efficient ML production system. With ML Ops, CI/CD automation accelerates experimentation and ensures consistent delivery of pipeline updates to production. How it works? First of all, development and experimentation. Data scientists experiment with new features, models, and hyperparameters. Their work results in updated source code, and this source code is published to a repository. This experimentation benefits from the orchestrated approaches we discussed earlier. Then the continuous integration. Every time code changes, the CI procedure builds, tests, and packages pipeline components. And this includes unit tests for data transformation and model logic, ensuring training convergence and avoiding errors like nonce values, and validating compatibility between pipeline components. Then continuous delivery. This stage deploys the pipeline and trained models to target environments, automating processes like verifying model compatibility with infrastructure, load testing the prediction service for performance and latency, and validating data for batch predictions or retraining. Automated triggers. The pipeline executes automatically, either on scheduled or in response to monitoring alerts, retraining the model and updating the registry. And monitoring. Live data feedback ensures deployed models are meeting performance targets. Any issues like data drift or degraded metrics trigger new pipeline iterations or experiments. This entire process ensures that models not only stay accurate and relevant, but also adapt to rapid changes in data and business needs. CI/CD pipelines tie together all concepts we have discussed so far, transforming them into a unified automated system that is scalable, reliable, and easy to iterate on. In short, this is how you bring together data, experimentation, infrastructure, and monitoring to build a foundational ML system that thrives in production. Imagine deploying a customer churn prediction model. The pipeline might extract user activity data from the feature store, validate and pre-process it, then retrain the model weekly. If the monitoring system detects a significant drop in accuracy or new patterns in user behavior, the pipeline triggers retraining automatically. This slide builds on the concepts of the CI/CD automation we covered earlier by breaking down the stages of a fully automated ML pipeline. Let's walk through each stage in the process. The first one is the development and experimentation. This is where it all starts. Data scientists experiment with new algorithms, feature engineering, hyperparameters, and these experiments are orchestrated to ensure consistency, and the resulting ML pipeline code is pushed to a version control repository, serving as the foundation for the CI/CD pipeline. Once we have this code, then the pipeline of continuous integration starts. So unit tests for feature engineering and model methods are included. Verifications that the model training converges without errors. Integration tests are passed to confirm compatibility between pipeline components. And the output is a collection of pipeline artifacts, packages, executables, and other components ready for the next stage. And the next stage is pipeline of continuous delivery. And in this step, the artifacts from the CI, continuous integration, are deployed into the target environment, creating an automated pipeline. This pipeline is tested and it can be staged to production-like environment. And then the automated triggering. The pipeline is designed to execute automatically based on specific triggers. Then model continuous delivery. Once a model is trained, it is deployed as a prediction service. This includes verifying that the model meets performance and compatibility standards, functions correctly when interacting with the service APIs, and performs efficiently under load conditions. Then the monitoring. It's a critical stage, and real-time statistics on model performance, such as prediction accuracy, latency, and resource usage are collected. Also, data drift or performance degradation is monitored, and so they can automatically trigger pipeline re-execution. Of course, there are manual steps. It is worth noting that while much of this process is automated, some steps remain manual, such as data analysis and reviewing model analysis result. This pipeline enables rapid and reliable updates to production systems, allowing organizations to keep up with the dynamic data and changing business needs. It also ensures that the model remain accurate and aligned with real-world requirements. And by combining automation with manual oversight at key stages, the pipeline balances efficiency with quality control. Let us now talk about non-technological side of ML projects. And we will cover business alignment and value creation, responsible AI, stakeholder engagement and communication, and team dynamics and collaboration. So this slide summarizes critical aspect of any successful ML project, moving from clarity to impact. And the first thing that should be staged is project clarity. Every successful project begins with a clear understanding of the problem you are solving. This means asking the right questions. What are the objectives? What does success look like? What are the success criteria? And are we addressing a real need or just creating a technical solution without impact? This clarity ensures that efforts are focused on meaningful outcomes. Team efforts direction. Once the problem is clearly defined, the next step is aligning the team's efforts. Everyone, from data engineers to business stakeholders, needs to work toward a common goal. Misaligned priorities often lead to wasted time and resources. So, maintaining direction is key. Technical excellence. Here's where the actual ML works happens. The team must focus on delivering technical solutions that meet high standards of quality, scalability, and reliability. However, technical excellence on its own isn't enough. It has to align with the project's objective and meaningful and measurable outcome. The final goal of any ML project is to create a measurable impact. This could be improving key metrics like revenue, reducing churn, or streamlining operations. It's essential to ensure that these outcomes are not just theoretical but can be tracked and validated. And key insights in the red box. Always validate your hypothesis to ensure that you're solving the actual problem and not automating something overly complex or poorly engineered. Just ask yourself, are we solving the root problem or just adding layers of automation? Is this solution efficient and necessary? It's easy to get lost in over engineered processes or irrelevant technical complexities. Avoiding this trap ensures that your project remains focused and impactful. Imagine an e commerce platform aiming to reduce cart abandonment. So if the project focuses only on predicting the abandonment without addressing why user abandoned carts, like poor UI or unexpected fees, it is solving the wrong problem. This is why validating hypotheses and ensuring alignment with user needs is critical. Successful ML project, it isn't just about technical excellence. It's about solving real problems efficiently and delivering measurable results. And keeping these steps in mind ensures clarity, direction, and lasting impact. As AI systems become more integrated into decision making processes, adhering to the responsible AI principles is not just best practice, it's a necessity. Let us walk through these principles of fairness. Eliminating bias in data and models is essential. Bias can creep in through imbalanced data sets, flawed assumptions, or overlooked variables. A model that discriminates, whether intentionally or unintentionally, can cause significant harm to individuals or groups. Transparency. Transparency ensures that AI decisions can be understood and interpreted. This involves explaining how model works, what factors influence predictions, and why specific decisions are made. Transparent AI builds trust among stakeholders and users alike. Imagine a loan approval model. Transparency allows applicants to understand why their loan was denied and what they can do to improve it. Accountability. Documenting processes and assigning responsibly ensures that there is always someone to oversee AI systems. Accountability is critical when things go wrong, whether it's like misclassification or system failure. For example, creating clear audit trails can identify the origin of errors and allow teams to act quickly. Privacy. Protecting sensitive user data is a legal and ethical requirement. Privacy preserving techniques like differential privacy and encryption ensure data security while enabling the model to function effectively. This is especially important in sensitive domains like healthcare or finance. And safety. Safety involves testing models for robustness and avoiding harm. This means accounting for edge cases, unexpected inputs, and potential misuse. For instance, a self driving car's model must be tested to ensure it behaves safely under all conditions, not just ideal ones. And embedding these principles into your AI projects builds trust with users, stakeholders, and society as a whole. It ensures that the systems you develop align with values and organizational goals while minimizing risks and unintended consequences. For those interested, Microsoft's Responsible AI Standard provides a detailed framework to implement these principles. You can access it through the link or you can Google it up. In summary, responsible AI is about ensuring that technology serves humanity, avoiding harm while maximizing benefits. And by integrating these principles into your ML workflows, you set a foundation for sustainable and solid development. Let's talk about cost optimization and return of investment, two crucial considerations for sustaining ML projects in production. So, what about optimization costs? Um, you can use serverless architecture. Serverless solutions can save costs by dynamically scaling resources to match the workload. You only pay for what you use, making them ideal for handling fluctuating demands or infrequent model usage. Streamlining data pipelines. Efficient ETL, extract, transform, load processes reduce unnecessary computational overhead. For example, using tools like Apache Spark or Airflow can ensure that only relevant, high quality data reaches your model, minimizing both processing time and costs. Balancing model complexity with performance. A more complex model doesn't always translate to better results. Simpler models are faster to train and deploy and often meet performance requirements with significantly lower costs. Consider using techniques like model pruning or knowledge distillation to reduce complexity while maintaining accuracy. What about return of investment? So, how to maximize it? Regularly assess business impact. Evaluate how your model aligns with business goals. For example, it's driving higher sales, reducing churn, or improving operational efficiency. This regular assessment of the ML system uh, delivers value beyond just technical metrics. Just take an audit and review. Are you aligned with the business goals? Prioritize high impact efforts. Focus your resources on tasks that provide measurable outcomes. For instance, instead of spending months improving a model's accuracy by half of percent, invest in optimizing deployment pipeline to scale the system or enhance the user experience. In ML production, every dollar spent should contribute to a measurable result. By adopting cost-efficient architecture, simplifying processes, and aligning ML goals with business outcomes, you ensure sustainable operations and stakeholders' confidence. Imagine a recommendation system for an e-commerce platform. By switching from on-demand GPU instances to a serverless framework for real-time inference, the company can save X% in operational costs while maintaining the same user experience. At the same time, tracking metrics like revenue uplift from recommendations help justify further investments. Cost optimization and return of investment assessments aren't just like technical decisions. They're strategic moves to ensure long-term project viability and success. Let us now turn to stakeholders' communication and team dynamics, both critical for the success of any ML project. These aspects ensure that your technical efforts align with organizational goals and that teams work to deliver impactful results. What about stakeholders? Set realistic expectations. Begin with clear explanation what ML can and cannot do. Often, stakeholders may have unrealistic expectations like achieving perfect accuracy or immediate results. Explain the iterative nature of ML and its dependency on data quality, availability, and involving requirements. Just an example, for a sales forecasting model, clarify that while it can predict trends, external factors like sudden market shifts may still affect accuracy. Use non technical language. Not all stakeholders are technically fluent. Translate complex concepts into relatable, simple terms. For instance, instead of saying the model has an F1 score of 0.85, explain it. Our model makes accurate predictions 85% of the time, balancing prediction and recall effectively, and include diverse perspectives. Involve cross-functional teams like business, engineering, domain experts. These perspectives help identify overlooked biases, improve problem framing, and enhance the model's relevance to real-world applications. Example, in a healthcare project, combining insights from Doctors, data scientists, and administrators can lead to a more effective and deployable solution. And what about the team collaboration? First of all, encourage open communication. Teams perform best when they can freely share ideas, challenges, and concerns. Regular check ins and clear documentation of processes help ensure everyone stays on the same page. Example: implement tools like Slack for real time communication and Confluence or Notion for centralized documentation. And invest in tools and resources. Equip your team with collaboration tools like Git for version control, Trello for task management, and cloud platforms for seamless experimentation. Having the right resources minimizes bottlenecks and allows the team to focus on innovation. Why this matters? The technical success of an ML model means little without alignment with organizational goals and effective teamwork. Engaging stakeholders ensure their support, while fostering team collaboration accelerates the journey from research to impact. To sum up, strong communication and teamwork create an environment where ML projects thrive, not just technically, but in delivering real world value. Building trust with stakeholders and empowering your team go hand in hand with achieving scalable and impactful ML solutions. To ensure the success of an ML project, effective stakeholder engagement is critical. Uh, let's review some of the keys to success. And the first one is schedule regular interactions. Frequent, consistent communication is essential to keep everyone aligned. This could involve weekly progress updates, dedicated feedback sessions, or even informal check ins. Regular meetings ensure stakeholders stay informed and feel involved in the project's journey. Example: you might set up a recurring session with product managers to share the latest results and clarify priorities for upcoming sprints. Manage expectations. Set realistic goals about what ML can and cannot achieve. Many misunderstandings arise when stakeholders assume ML systems can solve problems instantly or perfectly. Clearly explain any constraints, trade offs, and timeframes to avoid disappointment. Example: for recommendation system, clarify that while it improves user engagement, it won't necessarily solve all customer retention issues. Gather insights. Stakeholders often possess domain expertise that's invaluable for refining your models. Use their feedback to align the project with business objectives and uncover nuances in the data or problem framing. Example: a sales team might highlight seasonal trends in customer behavior that your model should account for. And make the process inclusive. Ensure all voices are heard, from technical teams to end users. Diverse perspectives lead to better problem solving and decision making. For instance, a domain expert may notice a key factor overlooked in the initial modeling process. Example: when building a healthcare solution, include inputs from doctors, data engineers, and patients to ensure practical and ethical considerations are covered. And share transparent results. Trust is built through honesty. Share both successes and challenges. Highlight the progress made and also be upfront about limitations or areas for improvements. Transparency demonstrates accountability and fosters collaboration. Example: if a model underperforms during testing, explain why it happened, how you are addressing it, and the expected outcomes of the next iteration. Effective stakeholder engagement keeps your ML project on track aligned with business goals, and supported by key players across the organization. It also ensures that when challenges arise, the team can pivot with understanding and support rather than resistance. By following these steps, you will foster a collaborative environment where all parts feel valued and where the project is set up for both technical and business success. Creating a high performing machine learning team is about blending diverse skills, fostering collaboration, and aligning efforts toward clear goals. Let's dive into the key components. So, diverse experience. Effective teams bring together individuals with varied backgrounds, data scientists, engineers, domain experts. Example, healthcare project. Having clinicians work alongside ML engineers ensures that the models align with real world medical needs. Clear objectives. Without a shared understanding of the project's goals, efforts can become misaligned. Ensure every team member knows the purpose, deliverables, and success criteria. Collaboration. Promote open communication and teamwork. Engage different departments such as IT for infrastructure and business for strategy alignment. This cross functional collaboration is essential for end to end project success. Agile approach. Machine learning often requires iterations, testing ideas, gathering feedback, and improving. An agile mindset allows teams to stay flexible and adapt to a challenging nature of ML. And good tools and resources. So equip your team with the right technologies, whether it's data annotation tool, computing resources, or collaboration platforms. Efficiency depends on having the right support. And ongoing learning. ML is a rapidly evolving field. Encouraging continuous education through lectures, courses, conferences ensures the team stay ahead of trends and innovations. And responsible AI focus. Building ethical AI should always be a part of the discussion. This includes addressing bias, ensuring fairness, and being transparent about model decisions. Example, team working on facial recognition tool must ensure datasets are balanced to avoid biased outputs. Set success metrics. Define clear indicators of progress. For example, if you're deploying a recommendation system, metrics could include click-through rates or user retention. And leadership support. Management backing is crucial. Leaders should provide clear direction, allocate resources, and empower the team to make decisions. Without this, even the best team can face roadblocks. Building effective ML team is not just about technical skill. It's about fostering an environment where collaboration, clarity, and innovation thrive. This foundation enables teams to overcome challenges and deliver impactful results. Planning and managing machine learning projects require structured approaches to maintain efficiency and deliver measurable outcomes. And let's break this into two aspects depicted on the slide, the iterative cycle and prioritization. And the first one is iterative workflow of ML project. This cycle illustrates like several stages. You need to formulate, like identify problems and prioritize ideas. You could use something like ICE score, like impact, confidence, and effort. This ensures the team focuses on high value tasks. Then design, transform prioritized tasks into actionable stories, define methods and identify the data needed. Using Kanban boards help visualize and manage workflows effectively. Experiment. Test hypotheses by running experiments. Document findings to refine approaches for continuous improvement. And validate. Measure the impact of your models and experiments using well-defined metrics. This stage fits back into the formulation stage, creating a continuous improvement loop. And this workflow promotes adaptability, allowing teams to adjust priorities and strategies as new data or insights emerge. And you also need a prioritization framework. One of the prioritization methods is depicted here. It uses must-have, like crucial deliverables essential for the project success. Should have, important but not crucial. Could have, like nice to have items, and won't have, features or tasks explicitly excluded from the current scope. Buffers are added to account for uncertainties or unexpected challenges. And by combining fixed time boxes with this prioritization, teams can stay on schedule without compromising quality. And combining iterative workflows with prioritization frameworks gives you like a balance between agility and focus. Maintain a clear roadmap and constantly validate progress. ML teams, in this case, can navigate complexity and deliver impactful results. AI is reshaping organizational structures in different ways, shifting the focus from scaling headcount to scaling compute resources and automation. The traditional organizational model is on the left. You can see like structure of scaling businesses. Growth largely depends on the increasing headcount at various levels, from executive leaderships to teams in product, engineering, sales, operations, and finance. This often meant larger hierarchies, complex coordination, and significant overhead costs. Imagine like growing e-commerce company expanding operations to meet customer demand. On the right is AI-enabled organization model. With AI, scaling businesses now means scaling compute power and leveraging automation rather than merely adding more people. You see how AI plays a pivotal role with tools like AI copilots supporting or even replacing repetitive and scalable tasks. Leadership remains lean but is empowered with advanced decision making insights generated by AI. Teams like product and engineering or sales and marketing are now augmented by AI driven tools, enhancing productivity and reducing manual work. AI copilots take over routine functions in areas like operations, legal, and support, allowing human workers to focus on strategic and creative tasks. Imagine AI-powered customer support. It can handle thousands of inquiries in real time, reducing the need of a large support team while maintaining quality. And the key implications for businesses. This transformation enables companies to scale faster and more efficiently. By replacing labor-intensive processes with intelligent automation, business can maintain agility, reduce costs, and focus on human resources uh, on areas requiring creativity, critical thinking, and anything intelligent. And for employees, this meant shifting roles towards oversight, strategic planning, and creative problem solving. And for leaders, it requires a mindset change, understanding how to effectively integrate AI into workflows and making data driven decisions. This transformation not only changes how organizations operate, but also reshapes how teams collaborate and deliver value. As AI takes on repetitive tasks, businesses must ensure they are fostering innovation and creating opportunities for employees to grow in new directions. While working on machine learning projects, it's crucial to be aware of the potential pitfalls that can derail process. Those are common actually. So there are business objectives, and that's one of the most common pitfalls is misalignment of the project's objectives with the business needs. Sometimes team focus on solving interesting technical problems without fully understanding whether the solution drives value or meets a critical business goal. This leads to wasted resources and unmet expectations. And the key question here is are we solving the right problem that creates measurable impact? Technical challenges include data issues such as insufficient or poor quality data, lacks of reproducibility in models, and scalability constraints. Additionally, over-engineering solutions can lead to complexity that becomes difficult to maintain. And the key question here is, do we have the infrastructure and data to support solution? And human factors. Human challenges are often underestimated, but can be the most impactful. Lack of collaboration between teams, unrealistic expectations from stakeholders, or a failure that was not clearly communicated. This all can lead to friction and project delays. And team members might also lack the domain expertise or ML skills needed for the project. And the key question here is, are all stakeholders aligned, and is the team equipped to deliver? And AI factors, they are new if we're talking about like project pitfalls, and they are still like evolving, so they're not like solid because there are AI agents appearing, and we might face more factors like AI factors. But the most common ML pitfalls is bias in models, interpretability, reliability of models. And the key question here, are we building an AI system that really delivers the value, that solves the exact problem? Do we understand it? Let us sum up the keys for ML project success. To be successful delivering ML project, we need to focus on several objectives. The first one is business objective. We must start by focusing on impact. The goal is to solve clearly defined business problem, not just solve some technical challenge. We need to define success criteria, align business KPIs with measurable technical and project metrics. And continuous validation is crucial to ensure our solutions remain relevant as business needs evolve over time. And technical excellence. Keeping things simple is essential. We don't want to have over-engineered solutions that are hard to support. We should prioritize scalable and maintainable solutions. High quality, relevant data is the backbone of any successful ML project. So staying data-driven is critical. And additionally, choosing the right tools and techniques for the problem at hand ensures efficiency and effectiveness. Team and collaboration. Empowering the team is a priority. This means providing the necessary tools, resources, and skills for success. Collaboration across functions, bringing together domain experts, engineers, and stakeholders, ensures alignment and better outcomes. Iterating and adapting quickly helps the team stay agile and responsive to feedback. Execution and process. Effective planning is key. Breaking the project into manageable phases with clear timelines makes the process more structured. Monitoring progress through transparent dashboards and updates keeps everybody informed. And lastly, identifying risks early and having contingency plans in place ensures we can handle challenges smoothly. And by focusing on these areas, we create structured, efficient approach to ML projects that aligns technical excellence with business impacts while fostering strong collaboration across teams. I wanted to share some useful materials, so yeah, please use them. They might be relevant. Some of them are on system design or just on applications, but yeah, I find them really useful. Summing up the whole lecture, let us have the key takeaways. In this presentation, we have covered the critical aspects of implementing machine learning in production. It starts with turning research into scalable and reliable solutions that create real-world impact. We highlighted core challenges, including effective data management, ongoing model monitoring, responsible AI practices, and the complexities of scaling ML systems. We have emphasized why processes matter, from building robust CI/CD pipelines to continuous monitoring and retraining, ensuring the system remains effective over time. On scalability, we explored tools, distributed training, and automation, which help system grow seamlessly with business needs. Collaboration was another key theme. Aligning stakeholders, empowering teams, and fostering synergy between cross functional groups are critical to success. But all efforts must ultimately lead to business impact, solving real problems, aligning KPIs, and delivering measurable value. And finally, responsible AI ensures fairness, transparency, and safety in our systems, while a strong plan for success depends on effective planning, empowering the team, and executing with agility. Together, these principles provide a solid foundation for any ML project to thrive. Okay, so what we have explored today. Machine learning in production isn't just about building models. It's about creating systems that solve real world problems. It's about taking that spark of innovation and turning it into something scalable, reliable, and impactful. We have talked about core challenges from the technical perspective, and we have talked about collaboration between teams and stakeholders. But please remember, no ML project thrives in isolation. It's the alignment of stakeholders, empowerment of teams, and cross functional synergy that provides insights, that helps you create the system that brings impact. Let us not lose the sight of the bigger picture, the why. Every ML project must have a purpose, solving meaningful problems, aligning KPIs, and driving measurable results. That's where ML creates value. It should be transparent and safe, and don't forget about responsibility. As you go on your own ML journey, I want to leave you with this thought. Success in ML is not just about technical skills. It's about curiosity, adaptability, and commitment to making a positive impact. The tools and frameworks will evolve, but the mindset you bring to your work will always be your greatest asset. So go forward, use the power of machine learning to solve problems that matter. And remember, every great innovation starts with a question, and your journey is just the beginning. Let us build the future together, and thank you.